Hey, welcome to the Awesome Intelligence Podcast. Today, our guest is Mustafa Kaddoura. He earned his PhD from University of Minnesota in mechanical engineering, and he is working as a senior application engineer in ANSYS, where he works on computational fluid dynamics. To do his research, he relies on Hamiltonian neural networks, which is a specific type of physics-informed neural network, or PIN. Today, Mustafa will walk us through what is a physics-informed neural networks and how it relates to Hamiltonian neural networks and the idea of gray box. So let's get into it. For that, Mustafa, how are you doing today?
I'm doing well. Hi, Dipansha. Thank you for the introduction. And I'm happy to be with you in this podcast.
Awesome. So, Mustafa, if you can sort of give us an overview of, what is an energy system and what it is made up of, and how do you define an energy system and its inner workings?
Yeah, so energy system is any system that can generate, store, or convert energy from one form into another. And recently we are hearing a lot about energy systems because many governments and industries are working on the net zero emissions to reach zero carbon emissions, zero pollutants, and to reach a sustainable life. For that, we started hearing about renewable energy, green energy. So these are energy systems. They include wind turbines, solar energy, even internal combustion engines are energy systems, but they generate some pollutants. And currently we are talking about also hydrogen combustion, and like any system that can generate energy is an energy system.
And why do we care about net zero carbon emission, and why is it important to build this kind of energy system that produce net zero carbon systems?
Yeah, so I believe everyone on the globe have seen some kind of the global warming that we are seeing. We are having like climate change in many countries, and that's because of the greenhouse effect. So traditional energy systems releases carbon dioxide, which acts as a green effect, causing the planet to heat up. For that, we are working on reducing these emissions so that we have a sustainable environment to reduce emissions and all these good stuff.
Awesome. I was reading one of your chapters from one of the publications, and it mentions that an energy system has three components: modeling, optimization, and control. So if you can discuss those, tell us about what is modeling, what is optimization, and what is a control system to make an energy system. That would be awesome.
Yeah, so as engineers, we aim to develop and design efficient energy systems that can give us the operate at the highest efficiency with minimal input. So to achieve this design, we need a model. A model can predict the system performance. It can forecast the future. So using a numerical model or a data-driven model, we can predict how our system will be behaving under different operating conditions. So that's why modeling are important, so that to reduce the amount of experimental testing, reduce the cost, and reach the market faster and solve the problem before it happens. And after we have our model and we want to design our system, we need to optimize the system. And by optimization, we mean to enhance the operation of that system to achieve the best performance with minimal cost. And after we have optimized our system, we want to put it to deploy the system, to put it in action. And as it's operating, we need to control its operation, to keep monitoring it, giving it commands, and maybe make it a smart system that can control itself to maintain the optimal operation status. So
Right.
that's the process for designing any energy system. It starts by modeling, then going to optimization, and finally controlling it in real life to achieve the goal.
Interesting. So if you if you think about the modeling part, so is it just like the mathematical representation, like the inputs and the outputs that you're gonna get from the energy system? So just you know, just dealing, sort of making the equations. Is that it, or in terms of
Uh,
data-driven system, or is it different?
True. So it's you can think about it as a digital twin, that we want a virtual twin or virtual representation of our physical system on our computers. And there
Right.
are different approaches for that. We can use equations, and that's what we call physics-based equations. And we can use also data, which is now growing more and more, and use some machine learning approaches to represent our system. At the end, we need
Interesting.
a model or a digital twin that can represent our physical system and can tell us what will happen in the future. That's the main
Wow.
goal of modeling.
What is a digital twin, by the way?
Yeah, so recently we started hearing a lot about digital twinning. So as the name indicates, it's a digital twin. So you have a physical asset, you have a system, and you need a virtual twin for this asset on your computer. So let's
Hmm.
say you have a factory, you have built a factory or a process, and
Hmm.
we want a virtual representation, a virtual twin for this factory on my computer that will be operating in real time in parallel, and it will tell me what will happen in the future, how my
Hmm.
system will operate, whether my system will fail, like
Yeah.
can be used for predictive maintenance and
Yeah.
these purposes.
Interesting. And you also talked about, physics-based model and data-driven model. Can you sort of discuss a little bit about the differences between them, and like how do we use a physics-based model versus a data-driven model, and when do we choose which one?
Okay, so physics-based model is the traditional approach, which is based on physical equations that
Mm.
represent and describe our system. Data-driven models are based on data collected from either experiments or field measurements that reflect how the system will operate. In the past, we were relying mainly on physics-based models and like doing some physical equations like conservation of momentum and conservation of energy to represent our system.
Right.
Recently, in the last decades, machine learning have grew up in at a fast pace, and we were able to develop machine learning approaches based on the data that we are collecting. And that's when we started hearing about data-driven models. But both models have advantages and disadvantages, and it depends on what's available to you to choose which system or which model is best.
Hmm. Do you have any advantage of using a data-driven model over a physics-based model?
Yes. Let me first tell you what's the advantage of the physics-based model.
Yeah.
It's the physics-based model is based on physical governing equations, so it gives me more information about my system, and it's usually a
Yeah.
3D representation of the system, so I can get a lot of details. However,
Right.
the disadvantage of physics-based model is that they are computationally expensive. They need long time to run, so I can't
Hmm.
use them in real time. And also, they are based on several assumptions, which are like idealistic assumptions. So
Hmm.
they don't necessarily reflect the uncertainty that we will see in the field. On
Right.
the and here comes the advantage of the data-driven models, because we are building our model out of data, real data. So
Hmm.
these data will include the uncertainties and the real operation of the system. And
Right.
also, since we have a trained model, a trained machine learning model, it's very efficient to run it. So we can run it in real time. We can use it
Hmm.
for real-time control of our system. And here comes the advantage. However, there is also a disadvantage for data-driven models because they are limited by the observed physics. So they,
Yes.
in many cases, they fail outside the data that they are trained on it.
Yeah.
Advantage and disadvantage for these two.
Yeah, that is really interesting, and it sort of is also mentioned in your paper as well. And I was trying to think about why a physics-based model would be really slow. I'm guessing, and it's not a bad guess. I know that because I have worked in the Industry 4.0 settings as well. So and I worked with data-driven system, and the equations, the governing equations, were all non-linear,
Yeah.
and how you want to approximate the non-linearity depends on how complex you want the system to be. I'm guessing the same principle goes for your use case as well, right?
Correct. That's completely correct. So I do fluid mechanics, computational fluid mechanics, and
Right.
the physics governing equation for fluid flow is called Navier-Stokes, which
Right.
highly non-linear equation. So we don't
Yes.
have analytical solution for that. For this, we
Yeah.
use numerical solutions, which we call
Right.
them like finite volume method or finite difference method to
Right.
solve this and to overcome this non-linearity. So we reach out to
Right.
a numerical solution, which is an approximation. It's not an exact solution, but it's good enough for engineers to design system. And these solutions are very expensive. Some of them can take days to simulate a system. Recently, we are doing improvement for the computational hardware. So now we started hearing about the GPUs, which can
Yeah.
reduce the computational time like by factor of 5. However, it's still expensive simulation,
Mm.
especially if I want to control like a drone, for example,
Yeah.
or control a self-driving car. We need something that can run in seconds, not in hours.
Yeah.
That's the
So
limitation of
so you
physics model.
cannot make a real-time system using a physics-based model because the computational time is too high.
Correct.
Why is that? I'm trying to understand why the computational time for a physics-based model is so much. Is it because there are so many nonlinear equations involved in the system that it takes a long time to solve those high polynomial equations? Is that the reason?
Correct. So if I want to simulate a fluid domain, I will
Right,
discretize this domain into small elements, what
right,
we call like generating a mesh. So my
right,
mesh can be maybe 1 million element. So I will
right,
be solving a million equation for each iteration. So
right.
that's computations. So the advantage of that I will get a lot of information out of this
Yes,
small lot of details, but in some applications it's not good thing for that.
interesting. On Sorry.
Yeah, I can give you an example just to understand what's the difference between a physics-based model and a data-driven model. Let's
Yes,
say I'm
please.
simulating a solar panel, a
Yeah,
photovoltaic panel. If I will do it using physics-based equation, I will get a lot of information. I can get the temperature distribution, I
yeah,
can get the thermal stresses, I can get the effect of the wind, of the operating conditions, the produced power. Everything can be predicted from the physics-based model.
yeah.
However, if I build a data-driven model, it will just takes the solar irradiation and wind speed as input, and it will just tell me the produced power. So it takes less
Right.
input and give me less outputs. So if I am just interested in specific output, data-driven models are good. But if I want to study the system at all levels, then I need to go for detailed physics-based models.
Wow. Yeah, that is an awesome example. I love that. Uh, Also, in the paper, you mentioned something that caught my eye, and I sort of it stuck to me so much that I thought I'd ask you this. So it says that sometimes when you run a data-driven model, because it's driven by data and you don't know what kind of data you are curating, sometimes it can reveal some new physics. Like, is that true? Did it happen?
Yes. So data-driven models get data from the experiments, from real
Yeah.
life, and it's able to recognize some patterns and relations inside this data.
Yeah.
For that, sometimes we can observe a new trend that we didn't know about, and it can be related to undiscovered physics. Also,
Wow.
based on the patterns observed in the data, we can formulate a new hypothesis and we start studying it. Also, sometimes we can use it to refine our models, like
Yeah.
to correct what we already have, the equations that we already have. So sometimes it can reveal some unknown physics out of data, but we
Right.
need to have high quality data and enough amount of this data
Right.
to reveal the physics.
Wow, that is amazing. It never occurred to me. So it's really nice to see that it is possible to sort of discover new trends of physics just by, I think of machine learning as a pattern recognition model, because that's all it is, looks for patterns that matches some sort of forms. And it's crazy to think about the fact that just by understanding these new patterns, you can hypothesize new ideas about physics, which is really interesting to me.
Correct. It's like you have another brain thinking with you. So it's your
Right,
brain and your brain both collaborating to
right,
understand the physics.
right. So now the I was going through some of the ideas of physics based versus data driven, and there's this there's certain words in the literature that I sort of when I scoured through the literature that I could find in the limited time, that so the literature for the word for the physics-based model is a white box, and the data-driven model is black box, because you are not getting enough inference out of the data-driven model. Whereas in the physics-based model, it's a white box because you have a lot of inference, even though you are losing the computational time, but the number of inference you are getting is a lot more. And what's funny is that in the middle, they talk about a gray box, which is sort of the good of the both worlds. So talk to me about this gray box idea.
Yeah. So as you mentioned, we have the physics, the physics-based models, which are white box because it's transparent. We are using clear equations, and we have the black box, which we just have data. We don't know anything about it. So if we mix them together in the middle, we will get the gray box. And sometimes we call it physics-informed neural networks. So it's a neural networks that are informed by physics, in which we add to the training some physical constraints to respect the physics behind it. Because usually if you just try to predict the performance based on data, you will miss, or you will not be respecting the physics.
Yeah.
But adding some physical constraints and physical loads to your model and to your data will make your model more realistic. It will be combining field data along with physics that we know. And there is a lot of work going in this area recently.
Interesting. So it's physics informed neural networks. That's the idea, sort of the best of the both worlds of white box and the black box. Interesting. So is it like you put some constraints on the neural network during the training process? Is that the idea of a physics informed neural network?
It can be like that. And also we can use data to solve the physics equations. So instead of going through the integration and the traditional method for solving the equation, we will be using data for doing that. So in this way, we have the marriage of our traditional equations and our data. So that's what we have. We call it a neural differential equation, like neural PDEs or neural ODEs. Like instead of doing the traditional integration, we let the data do that.
Awesome. So basically the optimization is done by a neural network as opposed to a numerical solver.
Exactly.
Interesting.
Exactly.
Your expertise is in Hamiltonian neural network, but before we jump into that, what is Hamiltonian system and what is Hamiltonian equation?
Okay. So that I will go back to the 19th century. So
Awesome.
we had a famous scientist called William Hamilton,
Hmm.
and he introduced a new scalar function, and he called it the Hamiltonian
Yeah.
because of him, and it represents the total energy of the system, which is
Hmm.
the kinetic energy and the potential energy. And
Yeah.
what's interesting, if you differentiate this function, you
Hmm.
will get the position of the system and the
Hmm.
momentum of the system, which describes the system state.
Yeah.
And then after him, we started talking about Hamiltonian mechanics, which is like a new era of physics after the classical physics.
Yeah.
That's all in the 19th century. But like 3 years ago, there were three researchers. They were inspired from this Hamiltonian mechanics, and in 2019 they published a new method. They call it Hamiltonian neural network, which is inspired from the Hamiltonian mechanics. So in Hamiltonian neural network, they instead of directly predicting the new state of the system, we are predicting the Hamiltonian. We are predicting the total energy of the system.
Right.
And we are training our system and optimizing our neural network based on the Hamiltonian. And the reason for that, because most physical systems are based on conservation of energy equation
Hmm.
and conservation of momentum.
Yep.
Traditional approaches fails to conserve this energy or fails to respect the physics.
Hmm.
For that, they said we will put like an intermediate step. We will predict the Hamiltonian, which is the energy. Then after that we will predict the new state of the system. So implicitly we have conserved the energy or teach our neural network to conserve the energy. That's the idea behind it.
Wow. And that's how the Hamiltonian neural network sort of comes in.
Correct.
And how do you put the constraints on the Hamiltonian neural network then?
Okay. So the constraints comes in the loss function. So in the traditional neural network, we give it inputs, like which is the momentum and position. And the loss function, we compare the inputs, which are the data, to our targets.
Yeah.
So we are directly comparing the state of the system, the
Yeah.
input and the target.
Mm.
In the Hamiltonian neural network, we take the momentum and position, and
Yeah.
we try to estimate the Hamiltonian, which is the total energy of the system. Then we differentiate this Hamiltonian, and we train our system based on the differentiated function.
Yeah.
So in this way, the neural network will learn how to conserve energy because it's looking at the energy itself, not looking at the state.
Yeah. Okay.
So yeah.
Interesting. So what I understood from the video that you posted on LinkedIn as well, and I did some research on my own, and what I found is that instead of, like you said, defining the loss function with input and output, like the traditional neural network, you sort of parameterize the Hamiltonian equation, and then you optimize the differentiation of the Hamiltonian function with respect to the parameter, right?
Correct.
And why do you do that? Like, what benefit does it give you?
Yeah, so that's the advantage of the concept of Hamiltonian, that if you differentiate the Hamiltonian function, you will get the position and the momentum. So instead of directly predicting the position and momentum, we try to predict the differentiated Hamiltonian. So we are bringing the total energy into the training process. So we have like two steps. We first predict H, which is the Hamiltonian. We get the ingredient of the neural network. Then we do the optimization.
Right.
It's like having a step in the middle that makes our neural network to respect the conservation of energy. Like we are guiding you. There is energy here that you need to take care of. Don't care just about the new state, care also about the energy.
Right.
And it's a very new trend. It's just like 3-4 years old. And many researchers started looking at it because it's giving a very promising results.
Awesome. Where can you use this Hamiltonian system? Like, to what kind of problems do you solve with Hamiltonian neural network? If you can give me some examples of that.
True. So currently the work is limited to motion planning. Like when you
Okay.
have a dynamic system, let's say a drone or self-driving car, these systems are based on kinematics laws and conservation of energy laws. For
Mhm.
that, we want a neural network that can respect this physics. And mainly we are using it for motion planning for these robots or for these vehicles. Because in using traditional neural networks, the solution that we are getting is deviating from the true dynamics because it's not learning the conservation laws, the physics laws. But by incorporating the Hamiltonian in our training, we are getting better motion planning.
Mm.
So that's where the work is mainly focused on that. And we have
Right.
some interesting companies like Honda is looking at Hamiltonian neural network for their cars. We have also Google looking at that. So a lot of people are looking at it from dynamic system modeling. That's the current
Dynamic.
step.
Interesting to control drones. And so basically it's motion planning for self-driving
Correct.
cars, robots, and drones, and
Correct.
all that. Why are we using that for a motion planning? What is the reason for applying Hamiltonian in those applications?
Yep. So as I was saying that in the past we were focusing on the physics equations, but these equations like oversimplify the system. So we end up by a model that doesn't reflect the physics that's happening. It's very simplified. Then in the last couple of decades, we started looking at the traditional neural networks, which is the black box. And the model that we were obtaining was deviating from the true dynamics. So if we do the experiment, like we make the drone to go through a path, it will not follow the path that we wanted to follow it. For that,
Right.
we recently started looking at that by incorporating this Hamiltonian neural network to get a more predictive model. And the applications for having an accurate planning are very numerous. We want our robots to follow our instructions.
Right.
So that's the current state. But why I am looking at that? What's the reason
Yeah.
I'm looking at
Yeah.
Hamiltonian neural networks? So my background is mainly in fluid mechanics, and all what I do is CFD, computational fluid dynamics.
Yeah.
And governing equations for CFD are conservation of momentum and conservation of energy. That's all. For that, we are like predicting that Hamiltonian neural network can be expanded from dynamic systems to the continuum mechanics regime. So we are thinking,
Gotcha.
can we use Hamiltonian neural network to predict the motion of the fluid? So when you are talking about a drone, you are talking about solid body, like a set of solid bodies.
Yeah.
But when it comes to fluid mechanics, it's a little more challenging because like it's very difficult to predict the motion of fluid.
Yes.
However, all what we care about is the conservation of momentum and conservation of energy to predict the
Yes.
new position of the fluid.
Yeah.
And that's why Hamiltonian neural network is interesting for fluid mechanics. And that's why I am doing some research on that to see can we expand the current state of art to fluid mechanics and using it for our systems. We will see.
Wow. What do you even give the Hamiltonian neural network as input for this to apply it into fluid dynamics?
Yeah, so currently I don't have a solid answer for that. I can tell you what we are giving it for predicting the motion of, let's say, a drone. We just give it the position and the momentum. So we give it
Okay.
a set of initial states, different initial states,
Yeah.
and we use the H and N to predict the trajectory. And we compare the predicted
Okay.
trajectory to the real trajectory that we have in the experiment.
Interesting. I'm not sure if you have looked into it, but well, from what I understand, the current state of the art for motion planning is probably reinforcement learning,
Mhm.
and I don't know if you can incorporate reinforcement learning uh, with Hamiltonian neural network, whether it's possible or not. But like, do you know whether they compare with each other, or like, is there any relationship between these two systems? Because I'm not familiar with the math of Hamiltonian that much.
Yeah, I think it can be. So we can do like levels of training. Like we can have a shell having the Hamiltonian neural network that will guarantee that the energy is conserved. Then we have different shells of other models that
Yeah,
guarantee other quantities are being satisfied.
yeah.
So yeah, like in the couple 2 years, I was looking at something called learning predictive model, which
Mm,
used for motion planning. Like we want our robot to learn in real time and
mm.
learn from previous historical data. And here's the reinforced neural network or learning was being used. But very recently, they started talking about like what about having this Hamiltonian neural network? And yeah, they can be incorporated together, but
Mm.
it's still like a very new idea. Like a lot of people are doing research on that, and we are waiting to see the magic that we will get out of this.
That is amazing. Uh, because the data-driven model is sort of the backbone of Industry 4.0, I guess. Uh, what is your thought on Industry 4.0? And do you see, because now there is a lot of talk about Industry 5.0 as well in Europe, and here in Canada, uh, in especially in University of British Columbia, the Department of Material Science and Mechanical Engineering is actively looking into Industry 5.0, which is the combination of data-driven system, and so it's basically the sustainable data-driven system, so that AI doesn't replace human workers completely.
Mhm.
So what's your thought on Industry 4.0, and do you see any change in the United States towards Industry 5.0?
Yeah, so currently, like all industries in the US started talking about incorporating AI and generative AI
Yeah,
into their planning.
yeah,
So we are no more looking at like a pure modeling. We started looking at how AI can enhance our model, make it
mm,
faster, make it more predictive. All
yes,
people are looking at this.
yeah,
So it's going very fast, and yeah, things are changing very, very quickly.
and the results are
So
pretty good, right? I mean,
correct,
the data-driven model, the outputs from data-driven model are really stunning.
correct, correct. So now we have the ChatGPT and these similar models that you can talk to them and they can tell you what to do. And
Correct.
these are based on language, on natural language processing. And what we are doing from engineering point of view, if a machine can understand language, then how can we use its power for modeling our systems and
Yeah.
having more predictive models for our systems?
Yeah,
And
100%. I mean, even though language models learn language, in the back end, you have a transformer. And basically, you can use a transformer to train anything, starting from a language to an image to maybe a sequence of instructions, right?
correct, correct.
So you can use a transformer to generate motion planning for a fluid as well,
Correct.
theoretically speaking.
Correct. We believe that will come and that will be happening in the future, but we are still working with that, like doing a lot of research to achieve to this point. but I believe it's coming. It might be a couple of years, 5 years, but for sure it's coming.
That is amazing. And uh, just to shift gears a little bit, because we have talked about all the technical stuff, and we still have a little bit of time left in our hands. Tell me about your journey. Where did you grow up, and how did you end up in the United States, and how was it like throughout this journey?
Yeah. So I was grew up in Lebanon. Originally, I am Palestinian, but I grew up in Lebanon. I did my undergrad and masters in Beirut, and then I decided to improve, like to work more, do more research. For that, I decided to come to here to University of Minnesota, and the reason for choosing Minnesota because like two of my books that I was using in my masters was
Mm,
authored here at U of M. That's why
awesome.
the motivation. So I then jumped into U of M and I did my PhD, and it's a great place. And directly after that, I joined ANSYS. So ANSYS is like the industry leading simulation software. And in the past, it was focused on physics-based modeling. But recently, we started looking into the data-driven approaches and how to get this marriage between data and physics. And we
Correct.
started talking about the digital twins. And that's what I'm doing currently with them. So we
Awesome.
are trying to capture the power of AI in our simulations to get better industry solutions.
Wow. That is really interesting because the application of computational fluid dynamics is not only just the oiling industry. There are some applications in uh, film industry
Many.
as well, believe it or not.
Correct,
Because
correct.
recently I was working at a film studio, so
Yeah,
uh, the application of fluid dynamics or, or fire and smoke, that is another really big application of dynamics in
yeah,
using AI in CGI. It's massive.
yeah. Have you watched Moana?
I have,
The
yeah.
movie by Disney.
Yes,
So all water splashing in Moana
yes,
are TFD simulations. So we are no
yes,
more drawing the water splash. We are
yeah,
simulating it. So we are seeing the real splashing patterns
yeah,
in the movie, in the cartoon animation. And
yes.
that's very exciting to me as well.
Yeah, and things are looking pretty good. Although it's computationally really heavy,
Right.
I do know some people on LinkedIn, and I'm hoping to interview them as well, who are focused on the simulation of fluids of a certain type, and that's the only thing they do.
Yeah,
And because I think there is a huge application of fluid dynamics in a lot of
phenomenal.
other spaces that you probably traditionally wouldn't think about,
Correct.
right?
That's true. True. Yeah.
Awesome. Talk to me about how you got into powerlifting and bodybuilding.
Okay. Yeah, so I was an athlete since like early age, and
Awesome.
during my undergrad at Beirut Arab University,
Mm,
I started to take this more seriously, take powerlifting and bodybuilding more seriously. And I have competed twice at the level of the university and at the level at the country level. And actually, bodybuilding have contributed to my career. I have
100%
to
agree with that.
credit that. Yeah. So in bodybuilding or in sports in general, you learn to be dedicated, and you learn that each goal needs to have a specific training program and a specific timeline to achieve your
Yes.
goal. So if you want to build a muscle or if you want to get a specific shred in your muscle, there is a
Yeah.
way of doing that. It's not magic. You need
Yeah.
to learn, then to apply what you have learned, and that's actually have contributed for my career. So now I know that every goal I want to achieve, I need to have a clear plan, and I need to be realistic to have a timeline for my goal to happen. It would not happen in a day and night. So that was a lesson I learned from bodybuilding. Actually, also bodybuilding have contributed to my presentation skills because bodybuilding is a show sport. So if you want to win a show, you need to be confident. You need to impress the people in front of you. It's a show. And that's what we do every time we publish a new paper or propose a new research method. It's like going into a show. You need to present it to people, to present it to the experts, and you need to convince them. You need to make them impressed. So it's like a show, and that's something also I learned a lot through bodybuilding. For that, I always encourage young students to get some extracurricular activities. Can be sport, can be anything else. But
Yeah.
getting these extracurricular activities and sports and competitions, they are part of building their career. So your
Yeah.
career is only built inside the classroom and lectures. There are other skills in parallel that you need also to work on to get the most of yourself, to be the best version of yourself. That's why I always encourage, like every time I see a new student, I encourage them to do sports, to do arts, do what they want to do, because that will make them dedicated, and that will be an early exposure to life, to real life, like how to achieve the goals.
That is brilliant. Really, really well said. I think bodybuilding teaches you discipline. It teaches you self-control,
Yeah,
and like you said, planning, which is, as you and I both know, a competition prep takes probably 20 to 24 months.
okay.
Sorry, 24 weeks at
Yes,
least. So it's
3 months.
yeah, so 6 months of prep, and then you have to plan how you're gonna get into the prep.
And you need to be
So
patient and to go through failure and success to
right,
achieve what you want. And that's life, actually. But you are testing life at small things, like
yeah,
at sport things. That it's good to learn there.
yeah, 100%. That is really well put. Awesome. That's all the question I have, Mustafa. Do you want to leave us with some parting thoughts before we end the podcast?
Some thoughts about uh I'm actually like everyone, I'm very interesting to see where the generative AI will take us, and I'm looking for having more sustainable communities
Hmm.
and more sustainable industries so that we maintain our environment and maintain our health. And it was a pleasure to talk to you and be in your
Seb,
podcast. Thank you very much for the invitation for that.
if you are watching this, you have made it to the end of the video. Thank you so much. I really appreciate it. But there is one more thing you can do to help grow my channel. Please click on the like and subscribe button. It helps the YouTube algorithm to take my channel to a broader audience. I hope you like this video, and if you want to watch more of this kind of video, please click on one of those video links on your screen right now. Thank you so much.